Welcome again to the fifth video on our series on industrial AI. Again with me here Rahul from company Tvarit, and in this video we want to focus on low latency applications. So in the fourth video we've seen different strategies of deployment, and now we want to think about the use cases behind the deployment where you have the requirements of very low latency. Rahul, can you give us a little bit of insight from your experience where low latency applications are useful and necessary?
Yes, definitely, Fabian. So low latency applications are very important use cases in industrial domains. And I think all of us, all the developers, they are definitely aware of one low latency application in automotive industry, in mobility industry. What is that? Let's think. This is pretty easy. Okay, so the application is autonomous cars. This topic is so famous nowadays, everyone is talking about it. In developer community, this is one of the most important topic, by the way. Yeah. So what happens when it's on pedestrian lanes, there is a person and all of a sudden, by the way, out of the bushes, and then all of a sudden our industrial AI system has to react very fast. Exactly same kind of applications also exist in industry. That's what I am going to give one example here. Drilling. Drilling is an example from machining industry. It exists literally in every application, be it automotive, be it sheet metal industry, be it, let's say, packaging, food, etc., etc. So drilling is very important. Here, in this example, I would like to show usually a tool when it breaks. How does it happen? Before tool breakage, the drill look like this, and after the breakage, tool look like this. Now let us try to predict this tool breakage. How would we predict? Can you think? Okay, so one idea which will come to your mind, which is going to be very simple idea. The idea would be this drill is consuming some power, and the power is in the form of current and voltage. You measure the input current and voltage, and essentially also this current and voltage you can also finally correlate it with the spindle power of the drill. Now if you do if you use, in fact, from Tvarit industrial AI framework, you can use ready-made tool breakage application also for drilling. You would realize there is a certain pattern in the behavior of current. As and when your tool is deteriorating, the current will start showing some spikes, and those spikes can be captured via dynamic learning. AI is all about, by the way, dynamic learning. And this dynamic learning eventually also helps us almost up to 48 drills in advance, a probability of this tool breakage, this drill breakage. Amazing, right? And how can this help? This can definitely help also in our logistic planning, in our tool remaining useful life related use case, also in inventory. Inventory is a very important concept in the tools industry. Let us understand one more example. Perfect. Okay, so what is the second example? This second example now is from cold forming industry. In cold forming, what happens is you have your input wire. This wire is coming here, and it goes the input wire is coming here, and it goes through various die. Step number 1, 2, 3, 4, and finally the product gets out. Yeah. Now here you would analyze. You would already guess a fastener manufacturing industry is again one of the most important low latency application. Fastener manufacturing, the speed is almost up to 2 to 3 fasteners every second. And every second, the machine control has to be so fast that it takes decision. If, let's say, something is going wrong in the process, it has to take decision like within millisecond level. And this can only happen with the application of fast data processing, big data processing, and at the same time, what Fabian explained us in the last part about the deployment near the edge, near the control. If you do the deployment of such kind of intelligent systems near the edge and near to the PLC, life is going to be fantastic. It's going to be much simpler. Let us understand again from Fabian, how does it happen?
Well, so let's now go down a little bit more to applications that are not in the millisecond range, but in the microsecond range, and also require high deterministic behavior. Now let's couple a neural network with motion control. So the application is like this. So we have here our XDR system, we have a conveyor, and we place products on this conveyor. So what we try to do now is we want to synchronize those little movers to products on the conveyor. And inside this red synchronization area, after leaving the synchronization area, we can go all the way back to point PF to synchronize again to the next product. Now let's think about, we want to train a neural network that realizes this concept, but with side constraints, like we want to do this where optimal and energy optimal. And so the basic idea is we have to capture, first of all, data. In this case, we use simply the TwinCAT scope and capture data of the initial point here, the final point, including the dynamics like velocity, position, and acceleration, and also different time spans, delta t, when do we need to be at point PF. And then we started learning. In this case, we generated labels based on a model, similar to what Tvarit already told. They also used a FEM model. In this case, we used not an FEM model, but a more easier way of modeling, and used these models and an optimization algorithm to generate targets, to generate labels for all those requirements that have been recorded out. And then we used basically a standard neural network, multi-layer perceptron, to train in this behavior into a multi-layer perceptron, exported an ONNX file, and integrated this into the PLC. And basically, we only need to have a look into our machine learning library, just instantiate a function block, use the predict function, and we have an inbuilt hard real-time inference engine in TwinCAT. And every time when the mover leaves the point PF, we calculate in hard real-time in one cycle the complete path for how to go from PI to PF. And this is how it looks like. So on the right-hand side here, you can see a non-optimized XTS system. On the left-hand side, you see the neural network optimized system. On the right-hand side, you can see the movers accelerate much faster than on the left-hand side. So on the right-hand side, we use a standard approach, which is the sync early strategy in our NC. It realizes the very same thing. So in the middle, you can see the movers, they all synchronize nicely to those black lines on the conveyor. So they realize the same, but in the end, because on the left-hand side, we have much smoother movements, we realize the same task with less energy consumption and, of course, with less wear. So let us summarize now the fifth video. Rahul showed us two applications for low latency use cases and how to integrate them. Then I had another example in the deterministic integration, so deterministic application in the microsecond range. And all of this was possible by using TwinCAT machine learning. So please, if you have any questions, don't hesitate to contact us. Visit beckhoff.com or beckhoff.ai, or of course tvarit.com.
Thank you. Thank you very much from my side as well. Nice to have you here in this video. Please take these high frequency use cases or these low latency use cases enthusiastically. They are very highly impactful. Thank you again. Thank you very much.